Hello everyone, welcome to the second class on orbital mechanics. So today's topic is Kepler's law of planetary motion and Newton's law of universal gravitation. So let us begin with the introduction. Okay, so the satellites are orbiting around the Earth in the same way as the planets are orbiting around the Sun. So Kepler has derived three laws describing the planetary motion. Later in 1665, Sir Isaac Newton has derived Kepler's law from his own law of mechanics and developed the theory of gravitation. Kepler's law applies quite generally to two bodies in space which interact through gravitation. The more massive the two bodies is referred to, the more massive of the two bodies is referred as primary and the other is referred as secondary, which is nothing but the satellite. Kepler's first law. So Kepler's first law states that the path followed by a satellite, that is the path followed by the secondary object around the primary object, the more massive object, will be an ellipse. So the first law states that the path followed by a satellite around the primary object is ellipse. We know that the smaller one is the secondary object, the larger massive one is the primary object, and the path in which the satellite is revolving around the primary object is an ellipse. Okay, so we know that ellipse has two focal points F1 and F2. The center of mass of these two bodies, which means the primary and secondary body, the center of mass of these two bodies together is called as a barycenter, and it is always the center of one of the focus. We have two focus for an ellipse, F1 and F2, and the center of mass barycenter will always lie in one of the focal point. So the mass of the Earth is very high compared to mass of the satellite. So under that case, then the center of mass, that is barycenter, coincides with the center of the Earth, which is therefore it is always at one focus. Which means again we can see that the mass of Earth is very large compared to the satellite. Under that case, the barycenter coincides with almost at the center of the Earth. So we can consider that the primary object always lies at one of the focus. So if we consider the Earth and Sun, we know that Earth is revolving around the Sun. So Sun is mass of the Sun is very high compared to mass of the Earth. And in that case, here the center of mass of these two bodies, that is Earth and Sun, when you take the center of mass lies at the center of mass of Sun. Okay. The eccentricity and the semi-major axis are the two orbital parameters specified for the satellites orbiting around the Earth. We have two major parameters that is influencing the path. One is the eccentricity, other one is the length of semi-major axis. Then for an elliptical orbit, the eccentricity lies within the range of 0 to 1. Here you can see that E is equal to root of A square minus B square by A, where A is the length of semi-major axis, B is the length of semi-minor axis. Kepler's second law. Kepler's second law states that the radius vector drawn from the Sun to the planet, so the radius vector drawn from the Sun to the planet sweep out equal areas in equal intervals of time. So it sweeps out equal area in equal intervals of time. As the orbit is not circular, we know that the orbit is not circular, the planet's kinetic energy is not constant in its path. So it has more kinetic energy at perihelion. It is also called as perigee point, and it has less kinetic energy in the apogee point. So perigee point is the point which is very closer to the primary object. The perigee point is a point in which the orbit is closer to the associated closer to the primary object. Whereas apogee point is a point where the object is far away or at the farthest distance from the primary object. Okay. So the kinetic energy is more when it is at perihelion, and kinetic energy is less when it is at apohelion. This implies it has more speed at perihelion and it has less speed at apohelion. If r is the distance of planet from the Sun, then the perihelion is r minimum and apohelion is r maximum. So you can see here in this example, we have a Sun here. So we have a farthest point here. So this is apogee point or apohelion. and this is the nearest point, which is nothing but our perihelion point. When this planet is coming here in the closest point, it has more kinetic energy. When it is going far away, it goes very slow. So here the planet is faster. Here the planet moves slow. So here it has more kinetic energy. Here it has less kinetic energy. Okay, so if this is R max, this is till the center, okay, R min, then R min plus R max is equal to 2a, that is 2 into the length of the major axis of an ellipse. Okay, it is 2 into the length of major axis of an ellipse. Now let us try to prove the second law, Kepler's second law. Okay, using the law of conservation of angular momentum, we can verify the Kepler's second law. Okay, at any point of the time, angular momentum can be given as m r square into omega. Okay, m r square into omega. So our angular momentum is nothing but the product of linear momentum into the position vector. So here it is also can be written as m r square into omega, where this m r square is nothing but your linear momentum, omega is the position vector. So now you can consider that there is a small area delta A described in short time interval delta t, which means we are considering a small area delta A. Let us consider any of this area. Let this area be delta A, that is swept in a very short interval delta t. Okay, so it covers an angle of del theta. Okay, let the radius of curvature of the path be r. Okay, the radius of curvature of the path, sorry, this is not radius of curvature of the path, the radius of this path be r. The radius of this path be r. So path radius is r. Here it is r. Since the distance del theta is very small, it is very small, we can consider that this is r and even this is r. Again, by using this sinusoidal law, we know that this distance here, this arc length is nothing but r del theta. So we can approximate it to a right triangle. So we can approximate the height of the triangle as r and the base of the triangle as r into del theta. Under that condition, so this is height of the triangle, this is base of the triangle. So under that condition, the area swept by the area swept in small time delta t is nothing but half into r, that is height into base of the triangle. So we have got this. Now when we are trying to when we are trying to find, this is the area delta A. This is the area delta A between the distance of r del theta, arc length of r del theta. Now when we want to consider the area traversed per unit time, then we are supposed to take delta A by delta t is equal to half r square into del theta by delta t. So we know that rate of change of phase is nothing but omega. We will see that. So now we are trying to apply limits when delta t tends to 0. So this del A del t represents difference equation, difference form. When this del t tends to 0, this will become differential form. So this will become dA by dt, that is equal to half r square into d theta by dt, whereas this d theta by dt is nothing but omega. Okay, this is nothing but omega. Now we can see that we have got dA by dt is equal to half into r square omega. I am trying to substitute r square from here. So what is r square? It is nothing but L divided by m into w. So when I substitute that, so we have r square as L divided by m into w. When I substitute that, I have dA by dt is nothing but L by 2m. So we know that the angular momentum is going to be same. It is going to be constant because due to law of conservation of angular momentum. The initial momentum is always equal to the final momentum. So because of which we have that L as constant, and mass of the object is going to be constant. So which states that the area swept per unit time dA by dt, that is equal to L by 2m, is a constant. So hence the Kepler's second law has been proved. So it sweeps. The Kepler's second law states that the secondary object sweeps due to equal area in equal intervals of time. So it has been proved. And we have also seen that when the secondary planet is orbiting around the when it is orbiting around the sun, then here when it is at the apogee point, we have the lesser kinetic energy. At the perigee point, we have higher kinetic energy. Okay, then we'll see Kepler's third law. Kepler's third law states that the square of periodic time of orbit is proportional to cube of mean distance between the two bodies. It states that square of periodic time of orbit is proportional to cube of mean distance between the two bodies. This mean distance is equal to the semi-major axis length, that is A. For artificial satellite orbiting the Earth, A cube is equal to mu divided by n square, where n is nothing but mean motion of the satellite in radians per second. So we can relate the period and n in such a way that P is equal to 2 pi by n. So this theorem states that A cube is proportional to P square. Okay, so it states that the cube of mean distance between the two bodies, the square of periodic time, is proportional to cube of mean distance between the two bodies. The mean distance is always equal to the length of the semi-major axis. So under that condition, A cube is equal to P square, is proportional to P square. Okay. So where n is the mean motion of satellite in radians per second, and mu is Earth's geocentric gravitational constant, whose value is given here. The shorter the orbit of the planet around the sun, the shorter the time taken to complete one revolution. This applies only to the ideal solution of the satellite, which is orbiting perfectly spherical Earth of uniform mass. So whatever laws we have studied, we have considered the ideal situation where the satellite is orbiting around the planet, which is perfectly spherical, and it has uniform mass, homogeneous mass distribution, and there is no perturbing force acting in the so around that there is no perturbing force acting. But in actuality, we have atmospheric drag, thrust, and so many forces acting, which are considered as orbital perturbations. But still, this law still hold to all the cases. Like even now, we are using this Kepler's law, this third law, to launch the satellite in the reality. The next topic what we are going to see is Newton's law of universal gravitation. So this is very well known law where when two bodies or two objects in space which is under the influence of gravitational force, it is governed by the Newton's law of gravitational force. So gravitation or gravity is the force of attraction between two bodies. All the objects in the universe attracts each other with certain amount of force, but in most cases the force is too weak to be absorbed due to very large distance of separation between them. So every objects or any the objects in the universe are attracted to each other by certain amount of force, that is nothing but a gravitational force, but we cannot feel the force since it is very weak in nature. Besides, the gravity's range is infinite, but the effect becomes weaker as the object move away. So it is the range of the force, the range to which the force, the gravity can attract is infinite. But as the distance passes, it becomes weaker. We never know where it will become zero. This force of attraction was first observed by Sir Isaac Newton and was presented as Newton's law of gravitation in the year of 1680. However, the gravitation can generally exist in two main instances. The gravitation may be attraction of objects by Earth. For example, if a body is thrown upward, it reaches certain height and falls downwards because of the gravity of the Earth. The gravitation may be the attraction of objects in the outer space. For example, the force between other planets and the sun. The force of attraction between other planets and the sun can be treated as the gravitation attraction in the outer space. Let us see what is gravitational force. So each body in the universe attracts other bodies towards itself with a force known as gravitational force. Thus, gravitation is a study of interaction of two masses. Out of these two masses, the heavier one is called as source mass and the lighter one is called as the test mass. The gravitational force is the central force which depends only on the position of the test mass and from the source mass. Always act along the line joining the center of two masses. It always acts along the line joining the two masses, center of the line. Joining the center of two masses. So the first is the vector representation. Second one is that the force is the function of r and it is represented by the unit product of unit vector. Here the force itself is described by the vector. Here it is represented with the unit vector r. Okay. So the core problem of gravitation has always been understanding the interaction between the two masses and their relativistic effects. So, according to Newton's law of gravitation, every particle in the universe attracts every other particle with a force whose magnitude is directly proportional to product of their masses. So, every particle, here Newton's law of gravitation states that every particle in the universe, and here particle is not a smaller particle, it means the bigger objects in the universe, attract every other object with a force of magnitude. So it attracts the other object with a force of magnitude that is proportional to the product of masses. Let us consider there are two masses m1 and m2. We have two masses m1 and m2. It is in the space. They are attracting each other by the force called as gravity, and this force is proportional to the product of two masses. It is directly proportional to the product of two masses. Again, here this same force is inversely proportional to the square of distance between the two objects. It is inversely proportional to the square of distance between the two objects, and the distance is taken from the center of the one object to the center of the other object. It is a straight line connecting center of one object to the center of other object. Here the straight line concept will vary when we come to the case of general relativity, but as of now we consider it is the line connecting center of both objects. Okay. Now, so we can put it together in the form F is proportional to m1 m2 divided by r square. To remove this proportionality with equality symbol, we are introducing a factor which is nothing but g. This g is nothing but gravitational constant. Gravitational constant. So here this f can also be represented as function of r. Okay, this f is variable because as it travels or as it propagates in the distance, as we move the distance from, like let us consider this is m1 and this is m2. This is m1 and m2. As we move farther, let us consider the m1 is extracting some force on m2. So because of m1 is attracting m2 by some gravitational force. Now, as we move farther, if m2 moves far away, this force will keep on decreasing. So, we know that this f is variable. The f is varied based on the distance r. Okay. So, as f of r varies inversely as a square of r. It is also known as inverse square law force. It is also known as inverse square law force. The proportionality constant g in the above equation is known as gravitational constant, and the dimensional formula of gravitational constant is mass inverse into L cube into the time period to the power of -2. The value of the gravitational constant in SI unit is nothing but 6.67 into 10 to the power of -11 Newton meter square kilogram per kilogram square. So it is Newton meter square per kilogram square, or in CSG unit it is 9 centimeter square per gram square. It is 6.67 into 10 to the power of -8. So the vector form of Newton's law of gravitation. Here we have two objects m1 and m2. Let us consider there is a force acting on the object object 1. So if I write F12, which means it is a gravitational force acting on 1 due to the object 2. Okay, so it is the first says that on which the force is acting, and second stated because of which element it is acting. Okay, this F12. So this F12 will attract M1 towards M2, which means the M2's gravitational force is attracting the M1 towards it. Okay, so the vector form of Newton's gravitational law of gravitation signifies that the gravitational force acting between two particles form action reaction pair. It forms an action and reaction pair. We'll see how it is. Okay, we have two vectors here. This is R1 and R2. This is a position vector of M1, which is R1, and here it is R2. The distance between M1 and M2 can be given by R21, which is nothing but R2 vector minus R1 vector. Similarly, so this direction is the vector. This vector is in the direction like from the direction of the vector is from M1 to M2. Whereas when the force is applied, so therefore the force applied on so this is from force applied on M2 by M1 it is. So the direction vector from this is M2 to M1. So therefore the force applied on M2 by M1, the force applied on M2 by M1 is given by F21. So as I said, F2 in the sense force is applied on M2 by M1 is given by minus, because the other one negative sign indicates it is an attractive force. Okay, so G M1 M2 divided by R21 square into R21. This is nothing but the unit vector. Similarly, now the force on M1 due to M2 can be given by F12, that is equal to minus G M1 M2 divided by R12 square R of 12. This is a vector. This is vector representation, unit vector on the direction of R12. Okay, now we can see that R12 is equal to R21 minus of R21, because they are acting in the opposite direction. So you have two objects M1, M2. So this M1 will attract, M1's gravitational pull will attract M2 towards it. Similarly, we have M1, M2. So the M2's gravitational pull will attract M1 towards it. So it is a force of attraction. That is why we have given negation. But when we want to replace this, so now we have stated the first is that we have seen the force on M2 by M1. And here we have seen the force on, this is M2 by M1. Okay, so force on, yeah, this is right. So the force on mass 2 because of M1. So it is vector from, so it is force extracted on mass 2 from mass 1. So that is written in this form. Now similarly, the force extracted on M1 by M2 is given here. So we know that this R12 is negation of my R21. So when I substitute it here, I have F12 is nothing but G M1 M2 divided by R21 the whole square into R21. This is unit vector. Hence, the applied force are equal and opposite in direction. Also, the gravitational force follows the Newton's third law of motion, which means they are action and reaction pair. They are action and reaction pair. Okay, so the gravitational force is explained by the Newton's law of gravitation. So the gravitational force decides how much we weigh and how much far a ball travels when thrown before it lands on the ground. For example, we are in the place of higher gravity, then we are pulled much towards the surface. Under that case, we weigh more. But when we are going and placing ourselves in the outer space or the place where the gravity is less, when we check our weight, we weigh less because of this gravity. And also also, like let us consider we are standing on the earth. We are trying to throw the ball upward. So under that case, when you have more gravity, it will travel a lesser distance. Whereas if you are in the place of lesser gravity, the ball will travel more height. This is why, because the earth is attracting the object whichever we are throwing. Okay, if the attraction is more, which means if the gravitational pull is more, the object cannot travel higher distance. It will fall in a shorter distance after going upward. If the gravity is low, then it can travel. The force of attraction is less, so it can freely move upward. So under the influence of gravity, it decides like how far a ball can travel before it lands on the ground. So according to Newton's law of gravitation, every particle in the universe attract each other particle with a force that is directly proportional to product of their masses, and it is inversely proportional to square of the distance between them. Mathematically, it can be represented as F is equal to G m1 m2 divided by r square, where F is the gravitational force between two body measured in the unit of Newton, G is the gravitational constant and its value is 6.674 into 10 to the power of minus 11 Newton meter square per kilogram square. m1 is the mass of one massive body in kilogram, m2 is mass of another massive body in kilogram, r is the distance of separation between two massive bodies. So the distance is measured from center of one object to the center of the other object. So the gravitational force follow the law of superposition. Okay, so Newton's law of gravitation answers only the interaction between the two particles. If the system contains n particles, there are n into n minus 1 by 2 such n into n minus 1 by 2 such interactions. According to the principle of superposition, if each of these interactions act independently and uninfluenced by the other bodies, then the result can be expressed as summation vector. So remember, each of these interactions are independent, it is uninfluenced by the other body. So only every two body has interaction and it is not influenced by the third body. Under that case, the superposition theorem will apply to it, which means the force on the first body or the second first with the third first with the fourth still first with the nth body can be added together to form the total force extracted by the object 1 on the remaining object. Okay, the resultant gravitational force is acting on the particle due to the number of point masses is equal to vector sum of forces exerted by individual masses upon the given particle. So now we can here derive Newton's law of gravitation from the Kepler's law. Okay, we know that force is nothing but mass into acceleration. So that can be given as here, suppose let us consider the test mass m and it is revolving around the source mass and the circular orbit. It is revolving around the source mass with a circular orbit of radius r with a constant angular speed omega. Then the centripetal force acting on the test mass for its circular motion is nothing but F is equal to m r omega square, where omega is nothing but 2 pi by t. Okay, so it is nothing but 2 pi by t. Kepler's third law states that t square is proportional to r cube. T square is proportional to r cube. When I substitute that here, then I have here I have to substitute that t square by r cube. So when I substitute this t square by r cube, I have 4 pi square. So this square will become here. So it is 4 pi square m r divided by k r cube. This r and this will get cancelled. So I have G is equal to F is equal to 4 pi square m divided by k r square, whereas this k is nothing but 4 pi square by gm. So that's F is equal to gm m divided by r square. So which is nothing but the Newton's law of gravitation. It can be derived from Kepler's law of motion. Okay. So again, this is again the final summary. So we know that Newton's law of universal gravitation, in which the force of gravity between any two massive objects is directly proportional to the product of their masses, and it is inversely proportional to the square of the distance between them. And the proportionality constant is g, which is nothing but the gravitational constant. Okay. So summary, we have seen that in the Kepler's law, the orbit of the secondary object around the primary is an ellipse, and the secondary object sweeps equal area and equal time, which means the secondary object has less kinetic energy at the point far away from the primary, and it has more kinetic energy at the point very close to the primary. And the third is that the cube of the semi-major axis is proportional to square of the mean periodic time. Okay, that is the third Kepler's third law. And finally, we have seen Newton's law of universal gravitation, which states that F is equal to g into m1 m2 by r square, where g is a gravitational constant, F is a force of gravity between m1 and m2, and m1 is mass of one object, m2 is mass of other object, r is nothing but distance of separation of the two objects. So with this, we'll wind up this lecture. So we'll see in the next lecture where we see about the two-body problem.